2, we're just looking at taking the derivative of various functions using a fairly long-winded process known as first principles. First principles is in the study design. You do need to know it. You'll be tested on it, and it'll pop up on exams as well. Let's look at our example that we've used previously about the fly and its displacement. Initially, the fly at the 1 second mark has a displacement of 4. 3 seconds later, so 4 seconds overall, there's a displacement of 19. If we look at the line that joins these two dots together, if we take the gradient of that line, it will represent the average velocity of the fly between 1 and 4 seconds. So it becomes pretty clear that to work out the gradient, we've got rise on run. So it's 15 divided by 3, and you can see there that there's an average velocity of 5 meters per second. And that's the calculation shown here. So no big surprise at all. If we're interested in the fly's instantaneous velocity, then what I would need to do is draw in a tangent line here. All right, so just drawing a tangent line to the curve at the point 14, and then calculate the gradient of that tangent line. And that will give us the instantaneous rate of change, or the instantaneous velocity of the fly at the 1 second moment in time. Now, we've got an average rate of change, that's the gradient of this secant here, and we have the idea of an instantaneous rate of change. This average rate of change is an approximation of the instantaneous here. What would make it a better approximation is if I brought this point in. So the closer I can bring this point in to this first point, the better the average rate of change will represent being approximately equal to the instantaneous rate of change at the position 14. Using just a general x and a general f of x, then I can look at those 2 points as being the point x comma f of x. So we had that as 14 before. And then if we went h units along later, so we had 3 seconds later, but we had h units along the x-axis later, then this point here is going to be x plus h. So it's just the x value plus the h here. And then we can work out the y value by simply substituting that into the f of x rule, so f of x plus h. Now, if we're trying to achieve what the instantaneous rate of change is here, if I can move that dot closer and closer and closer towards this first point, then what I'll end up doing is getting a better approximation for the instantaneous rate of change here. So you can imagine, and we've been through this before in class, but if I could bring that dot so it's just about on it, then calculate the average rate of change between the 2 dots, let's say it was here, then that average rate of change, if the dots are close together, is going to be a really good approximation for the instantaneous rate of change. Here, because it's further away, it's going to be pretty rough. So basically what we want to achieve here is to say, hey, what's the process for working out the average rate of change? And what can we do so that we can get the h to, in fact, be getting closer and closer to 0? So let's look at this. Average rate of change is going to equal the change in f of x over the change in x. So you can see here's our little rule here. So that position there for y would be f of x plus h. This position for y would be f of x, so it's f of x plus h minus f of x. As far as our run is concerned, we're going to have this position here for x would be x plus h, and this position here for x will be just x, so we're going to have x plus h minus x. and that will simplify to being just h. So that's the average rate of change. If we want to have an instantaneous rate of change, we want to move this dot so it in fact becomes right on top of the first one. That is, we want to evaluate this expression here, and we want h, the gap between the two dots, to be 0. But of course, if it was equal to 0, then the whole thing would be undefined because it's on the bottom. And this is where the idea of a limit comes in. What we're really trying to do is work out the instantaneous rate of change, and we do so by applying the limit as h approaches 0 of f of x plus h minus f of x all over h. We can't have h equaling 0 because then the whole thing will be undefined, but we can apply a limit. And remember, what are we asking here? What is this expression approaching as h approaches 0? We understand we can't have h equaling 0, but what is this expression getting close to as h approaches 0? Getting back to the fly situation, if I'm after the instantaneous rate of change here, then I need to have that, I'm basically working out the average rate of change as h approaches 0, so as this dot gets moved over the top of that dot, because then the secant will in fact become a tangent line at that point. So that's fairly heavy, but the process of evaluating it isn't too bad. It takes a little bit of work. All right, so if we've got a displacement function here, f of x equaling x squared plus 2, and we want to work out the instantaneous velocity, then basically all we're doing is working out the derivative. So this f prime of x just means the derivative, and it's providing us with the instantaneous rate of change for any value of x. So it's the steepness of the curve for any value of x. Here's our process. Firstly, just write down f of x. We then evaluate f of x plus h. So instead of writing in this rule with x, we write it in with x plus h, and then we evaluate. The derivative, the rule that will tell us the steepness of the curve for any value of x, that is the instantaneous rate of change, is going to be the limit as h approaches 0 of this here. So this is f of x plus h, that's f of x, and that's h. Get rid of the brackets, collecting like terms. Now this should always be the case. If you've done this correctly, then all of your top terms will have a h in it, and you'll be able to take h out as a common factor. And you can see I've done that here. We can now cancel out the h on the top line and the h on the bottom line. And so now what we're interested in is evaluating the limit as h approaches 0 of 2x plus h. So don't forget, you're subbing in for h equaling 0, not x. So you're just going to have h equaling 0, and there it is there. And that's 2x, obviously. So what have we just worked out? That f prime of x is equal to 2x. That's the rule. We're trying to work out what it's approaching for, what the instantaneous rate of change is for x equaling 1. So f prime of 1 is just 2 times 1, so it's just that rule there, and we sub that in. So it represents 2 meters per second. Overall, this is what we're dealing with. Instantaneous rate of change is equal to the gradient of the tangent line. The gradient function is a derivative. We call it the derivative, written like so. So this derivative is equal to the limit as h approaches 0 of that expression there, f of x plus h minus f of x all over h. Alright, so here we've got a problem where we need to work out the derivative using first principles. So for a, we've got f of x. We need to work out what f of x plus h is, so we can do that just substituting, instead of x, put in x plus h. Tidy it up. The derivative. So f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. We put in what f of x plus h is equal to. That goes in here. We put in f of x, we put in h. We then tidy everything up. Notice I do put it in brackets here, so I never make a mistake with the negative. So it's negative 6x, take away 7. A common mistake that kids make is to just go, okay, this is f of x plus h, and then go take away 6x plus 7. No, it should be take away 6x, take away 7. We now tidy up the top line, collecting like terms. And notice that we should always be able to cancel out the h that's on the bottom with the h that's on the top line. Always. So it just becomes 6. And then the limit as of a constant is always just going to equal that constant. And this makes sense to us because if we think about the original rule, f of x equaling 6x plus 7, then we know that that's a straight line with a gradient of 6. So what's the instantaneous rate of change going to be for all values of x? It's just the gradient of that straight line, which is 6. So it's sensible. Let's look at b, a little bit more work involved with this. F of x is equal to this quadratic. I now need to work out what f of x plus h is, so you can see I've got that there, squared, x plus h, again. I need to be able to expand that out, so it's x squared plus 2xh plus h squared. I've taken the 4 through here, and I've got the minus 1 still. And just tidying everything up, collecting like terms. The derivative is equal to the limit as h approaches 0 of all of that. I now put in x plus h, f of x plus h. I put in f of x, notice in brackets so I don't make a mistake with the negatives. I get rid of the brackets. I tidy up the top line. Notice that h is in each of those terms. So the h can be taken out of the top line. And we've got a h down the bottom, a h up the top, and that will always be the case, so I just cancel those out. And so now what I've got, the limit as h approaches 0 of 4x plus 2h plus 4. I now sub in for h, not x, but for h, and I'll get 4x plus 4. So what have I just found out there? For this parabola, f of x equals 2x squared plus 4x minus 1, the steepness of the line for any value of x can be worked out by this rule here. So f prime of x is equal to 4x plus 4. So how steep is the parabola? For x equaling 5, well, it'll be 4 times 5, which is 20, plus 4, which is going to be 24.